to see this, let us take a simple example of something like this, right. So, let us say you have lots of points, not necessarily the bank example, let us say it can be any example, lots of points which are, let us say, labeled as +1, and so I am using plus. Instead of using different colors, I am just going to use plus and circles for indicating two different classes. Let us say I have plus class here, and then I have the circle class, let us say here. Again, these are, so think of this as feature 1. This could be age, this could be anything, let us say it's some feature, and this is the feature 2 axis, and then you have data points like this. Now, what you also have, let us say, is a circle here and a plus here. Now, what happened is, I mean, what could have happened is there are a lot of pluses, but then this single circle on the plus side or single plus on the circle side could be potentially what you might call as, this might be an outlier, right. Why is it an outlier? Well, this is typically the plus region, or this is typically the circle region, but then a plus is there. This could be because somebody, while recording the historical data of banks, misrecorded the label information, right. So, maybe somebody who was asked to type out, all the features, enter it into a database, made a clerical mistake, right. So this which should have been a 0 now became plus. Similarly, this which should have been a plus now becomes 0. Now, what is the consequence of this mistake or this outlier, right? So, this is another outlier. These are outliers. Now, what is the consequence of this outlier? Well, let us say I have a test data point which I am going to indicate by shaded circle. Now, here is a test data point. Now, it is bang in the middle of the plus region. But now, if you are going to use the nearest neighbor method, now the nearest neighbor to this circle data point happens to be this circle, and so it will be labeled as circle. So, what happened is that by mistake, your nearest neighbor happened to be an outlier, and so you are incorrectly predicting for the test data point. So, in fact, if you look at, there will be some region around this circle, right. So, it may not be a circular region exactly, there will be some region around this circle where if you get any point, right. So, if you get a point in this region, what will happen is the closest neighbor or the nearest neighbor to any point in the shaded region, right. So, in the checked region is going to be the circle, and so you will actually make a mistake for if the test data point is in this grid, right. So, the checked region. Similarly, what might happen is there will be some region here, it will not be a circular region, it will be some kind of a polygon like this, but that does not matter. The point I am trying to make is that there will be this checked region, right. So, this will also be like a polygon of sorts. There will be this checked region where if you get a test data point, you are going to make a mistake. Now, that happened because your data is not clean, right. So, there are these outliers in your data, and in real world you always are going to encounter some sort of outliers or of some sort, right. So, there might be clerical mistake, it might be a mistake of let us say a sensor which is trying to detect your features, whatever it is, right. So, mistakes often happen in your training data, or there is an inherent uncertainty in your training data, there is some noise which you cannot control for, and so your data is always going to be messy. And now, as algorithm designers, we have to make sure that we do not succumb to this noise in some sense, right. So, now how can I fix this problem? That is the next question, right. So, I now understand that there might be these outliers of sorts. Let me go back to my data set as before. This was my data set, and I do have these outliers, but I do not want to succumb to these outliers. I don't want to make a mistake because there is an outlier. Now, how can I solve this problem? Well, pause and think about it. And again, one way you can do is one way that one answer that I typically get when I ask students this is that, hey, why don't we remove the outliers and then run the nearest neighbor algorithm? That seems like a very interesting case idea to do, right? So you just remove whatever is a bad data point and then run the algorithm with the good data set. But in 2 dimension, yes, you can see where the outliers are in some sense and then remove them. But the moment you have lot of features, which means the 100 features, right? So every data point becomes a point in a 100-dimensional space, and we cannot even visualize more than 3 dimension, right? So we are all 3-dimensional creatures. We cannot go beyond 3 dimension to visualize how things look like. So we can, it's hard to detect and remove these outliers when the number of features are, large. So we don't want to go that route to remove outliers and then solve the problem. Instead, can we somehow change the algorithm so that it becomes kind of robust to outliers? And for that, what will you do? Pause and think. I'll give you one potential solution to this, right? So one way to solve this problem would be to do the following. For every test data point, let's say this was the test data point, test point. If I relied on the nearest neighbor, I'm going to make a mistake. But what I'm going to do is, I'm not just going to ask a vote from the nearest neighbor alone, but I'm going to ask a vote from more than one neighbor. Let's say I asked a vote from 3 neighbors instead of just one, which means that I look at the top 3 closest points in my training data to this test point, and that would be, of course, the outlier here, and then that would be this point, let's say, and this point, right? So now these points become my top 3 nearest neighbors, right? 3 nearest neighbors. Now, what do I do with these 3 nearest neighbors? Well, each of them is going to give me a different answer potentially, right? So the outlier here would say, well, the label should be circle, whereas those other 2 points is going to say the label should be plus. So now I have 3 different labels to deal with. How do I resolve and make a single decision? The most natural thing to do then would be to do what? As you would have guessed, take the majority. Whoever has the majority, whether it is the plus or the circles, I will go with that. Now, if you really think, if it so really happens that this guy was an outlier, that outlier hopefully is not going to be in the majority. The name outlier is because it is not part of a majority, right? So it's some incorrect thing that has happened, right? So if a majority of things go wrong, then perhaps that's not an outlier quality, right? So that's in fact perhaps structure. So if you take the majority, then you can potentially fix this problem. Now if I take 3 nearest neighbors and I ask, hey, where are, what is going to be my solution? When for this test data point, I would actually predict plus, because 2 of the 3 nearest neighbors are saying plus and only 1 neighbor is saying circle, right? So I'm saying 3 nearest neighbor because 3 is an odd number, and if you ask odd number of people for their votes, now the majority will definitely be in one side or the other, right? So it will either be plus or 0. It will never be equal. Whereas if I ask 2 nearest neighbors and then one said 0 and the other said plus, then I don't know how to resolve the ties. So it's better to ask odd number of neighbors, and then you would resolve ties one way or the other. So the number of neighbors that you ask, whether should it be 3, whether should it be 5, we don't know, right? So now that number is what we are going to call as k. The number of nearest neighbors that you are asking an opinion for before you make a decision is the k value, right? So, and because you are asking k neighbors, this algorithm is called as k nearest neighbor algorithm. Now, let me state the algorithm again. Decide the label based on the decision of the majority of the k nearest neighbors, as simple as that. And we saw why k is important as well, and why nearest neighbor makes sense as well. The common issues with this algorithm are the following. One is choosing k, which is how can I choose whether it is 3 nearest neighbors I should look at or 5 nearest neighbors I should care about, right. So, and we will talk about this briefly a little later. The second is, how can I measure distances between data points? We saw the Euclidean distance is one way to measure distance, but is that the most natural thing always, right? So, depending on your features, you might have other distance measures which might be more relevant. Now, think about what other ways you might want to measure distances, and in your live session, maybe this is something that might be discussed in the live session as well. And finally, and perhaps the bigger issue here with this algorithm is that for every time I need to make a decision for a test data point, what are the steps involved? I should first figure out the distance of the test data point to each of the training data points, and then I have to sort them in increasing order of distance and then pick the top k. Now, if you had a million data points, let's say it's a big bank and the bank had last 25 years, it has had like million or 10 million customers. Now, for a new customer, I need to figure out who are the top 10 nearest neighbors. Let's say I decide to use k is not 10, let's say k is 11, it has to be an odd number. Now, I need to figure out who are the top 11 nearest neighbors of this new customer. But then there are 10 million customers in the bank history. So, I need to figure out the distance of the new customer to each of these 10 million people and then sort them and then take the top 11, and that is a very, very expensive computation. In other words, to make a final decision for any data point, you need all the 10 million data points to be available to you, right. Only then you can compute these distances. In other words, you have not really extracted out a model from this data set. You need the entire 10 million data points to make a decision for every new test data point, and that seems to be a very costly thing to do. So, these are some issues with the k nearest neighbor algorithm, and what we will do is and for this particular reason we will look at a slightly different algorithm which sidesteps this difficulty by not trying to retain all the 10 million data points once you have extracted out a model from this historical data. Only that model is going to be useful to make further decisions. You don't need the data set anymore. You can throw away the data set, and that's the power of a model, and we will see that in our next algorithm. Yes, just to summarize the nearest neighbor algorithms, you decide based on the majority of the k nearest neighbors. It's a simple algorithm. It's a wonderfully intuitive algorithm, but then it has its own issues, right? So, how do you choose k? How do you choose distance measures? These are choices that you have to make while you run the algorithm. But the more fundamental problem is, once, for every time you do a testing, you need the entire training data to be present. You have not extracted a model out of the training data. And that's the bigger problem with this algorithm. And we'll see how to fix this using one method that's the next algorithm that we'll start looking at. Okay.